Hi everyone, we are working on Taylor Polynomials and Taylor series today. So if you read the previous page, that just gives a little bit of application as to why this exists and why we're doing it. It works real well to approximate, especially transcendental functions. All right, so what I have here is a graph of sine of x. What I'm going to do is graph this approximation right here. Okay, this is actually a Taylor polynomial of degree 5. So we have three terms here, it's centered at 0. Okay, so it's going to come out in bold. So again, here's sine, and here is my approximation. Okay, and what's important to note is my approximation is centered at 0, and so around 0 it gives a pretty good approximation, but the further away you get, the further away it goes. Okay, and you could probably guess, but if I gave more terms, it would give a better estimate. Okay, so let's talk about how to actually find this Taylor polynomial. And it is this big, long, complicated looking formula right here. Okay, now the nice thing is a lot of things correlate. Okay, so for instance, the derivative that you're dealing with, so here this is like my second derivative, corresponds with this power, which corresponds with this factorial. Okay, those will always be the same. Right, so get used to looking at this, we're going to use this a lot. Okay, now a specific Taylor polynomial called the Maclaurin polynomial is just a Taylor polynomial centered at 0. Okay, so anytime you see Maclaurin, that just means that it's centered at 0. So in this case, c equals 0. The only reason why we have it named after him is because that came first. Okay, so first thing we're going to do is practice just writing a Taylor polynomial. Okay, so what I have here is all of my necessary information. Okay, so I'm just going to plug into my formula. Right, so I'm writing a third degree Taylor polynomial, which means that I need to write up to the third exponent or use the third derivative. And so you'll always have one more term than the degree. You'll have 4 terms here, unless something cancels out. But so my third degree Taylor polynomial is going to consist of f of 2 plus, sorry, that looks really ugly. All right, f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 divided by 2 factorial times x minus 2 squared plus f triple prime of 2 over 3 factorial times x minus 2 cubed. Okay, so this derivative, this factorial, and this power always correspond. Okay, this number right here and this number are just where I'm centered. I'm centered at 2. So now let's plug in the information they gave us. Okay, they said f of 2 is 3. They said f prime of 2 is negative 4. They said f double prime of 2 is 7. And they said f triple prime of 2 is negative 5. Right, and you could just write this as 2. You could simplify this to be 6, and that's totally fine as well. All right, let's do another one. All right, so this time we are finding the Taylor polynomial of degree 4 for this function. Right, so what I'm going to do is kind of write out some terms just to help myself organize. Right, so I'm defining f of x as e to the 3x. Hey, I'm going to need up to my 4th derivative, so I'm going to go ahead and find all of those right now. Okay, f prime is 3e to the 3x. F double prime is 9e to the 3x. F triple prime is 27e to the 3x. And then I need up to the 4th derivative is 81e to the 3x. And typically when you get to 4 is when you use your parentheses here. Okay, now I also need to evaluate each of these at 2, because that's where I'm centered. All right, so I need to actually know what f of 2 is, which is e to the 6th power. All right, and I need to know what all of these are, which is fairly mundane, but at least it's easy. Okay, so now I have evaluated all of my derivatives, and I've evaluated all my derivatives at my centered point, which is 2. That should be a 2. That should be a 2. Sorry. Okay, so now I can piece together my Taylor polynomial. So my polynomial of degree 4. So I start off with just my constant, e to the 6th, and then my first derivative divided by 1 factorial times x minus 2 to the first power, right? And then 9e to the 6th power over 2 factorial x minus 2 to the second power. Okay, those always correspond. 27e to the 6th over 3 factorial x minus 2 to the third power. Right, and then last one, 81e to the 6th over 4 factorial x minus 2 to the fourth power. Right, and that is our Taylor polynomial. I'm actually not going to simplify that at all. All right, next thing they want us to do is find the Maclaurin of degree 5 for sine of x. Okay, so I'm going to do the same thing that I just did. I'm going to go ahead and list out all of my derivatives. Right, and if you can't remember this stuff, remember you can do Snookum. And last one. Okay, so it cycles, and because it's a Maclaurin, I know I'm evaluating at x equals 0. Right, so I'm trying to find f of 0, which is 0. F prime of 0 is 1. Double prime of 0 is 0. Third derivative evaluated at 0 is, negative 1. Okay, and I mean, you might be asking, do I have to write it all out like this? I would recommend it just for organization's sake, because it can get confusing, especially if you have to write out a large degree like 5. Okay, now the nice thing is because all these zeros, a lot of stuff cancels, right? So as you piece this together, like your first term is 0. So that's going to go away. Your second term is 1 times x minus 0, so that's just x. Okay, your second degree is going to cancel. So then you're going to have a minus, and then x minus 0 to the third power, so just x cubed over 3 factorial. This is going to go away, and then your fifth is going to be x to the fifth over 5 factorial. Right, and there is a pattern here for sine and for cosine. Those are both important. Okay, now they want us to find p sub 5 of 1.4. So what they're asking us to do is plug in 1.4 in for x. All right, so that's going to be 1.4 minus 1.4 cubed over 3 factorial plus 1.4 to the fifth power over 5 factorial, which if you plug into your calculator, you get 0.98745. Okay. So now they're asking us to, if you plug 1.4 in for sine, what do you get? All right, so just sine of 1.4, which is very close. Okay, very close, a little bit of a difference. So they want us to find the error, which is symbolized by this. Okay, this is the actual minus the estimate, okay, in absolute value, because an error is always positive. We don't really care about the sign. And if you subtract these, you end up getting 0.00204, so a very, very small error. All right, for me, that'd be pretty acceptable. Okay, then they're asking us to do it again and kind of notice what point they picked. Okay, so we started with 1.4, and now they're asking us to evaluate at 2.1, okay, which is further away from my center. So remember, my center is 0. Okay, so at 2.1, I get 0.09684. Okay, the actual value of sine at 2.1 is 0.86321. Okay, so now I'm like way more off. Right, so if I subtract these, I'm going to end up with an error of 0.03363. Okay, and so something that I notice is that the error of my estimate at 1.4 is much smaller than my error at 2.1, right? And that makes sense because 1.4 is closer to my center. Right, so just like in that graph that we looked at the very beginning, the closer you are to your center, the better of an estimate or approximation it's going to be. Right, so here my error is much larger. Okay, and if we are trying to estimate, for instance, 2.7, which is even further away, my error will only increase. It's only going to get worse. All right, that is it for today. See you later.